Welcome to Aerospace Structures 1. In today's lecture, we're going to be covering the theory of elasticity, which plays an incredible role in the design of these structures to ensure that these structures are robust to the loading environments it will experience in service. The example we gave in the previous lecture that motivated the purpose of this course was the composite 787 Dreamliner. This Boeing aircraft composite structure had damage that occurred near the wings, at the wing body joint. And this failure or damage was unexpected. The theory of elasticity can help determine the root causes for these kinds of failures. It can help guide redesigns in the process of trying to improve the design so they can be more robust to the loading environments it's going to see in service. We'll be covering in this course the kinds of loads that these structures will experience in service. But there are many reasons why structures fail. We have examples of carelessness and error and negligence. As humans, we're not going to be perfect. Errors are going to be made. And it's important to minimize these errors because they can cost people's lives. And they can also cause significant amount of schedule delays and potential hits on the profits. So it's important to pay attention to the details when it comes to the design of aerospace structures. Another causes of issues is the insufficient strength. Failures can happen well below the strength of the material due to inherent flaws in the materials, or it could be due to fatigue loading conditions. These effects need to be accounted for. Another source of error when it comes to strength is that the strength allowable used in the design of the structure was perhaps not appropriate, and perhaps the measuring techniques used did not reliably measure that strength. Underestimation of loads is another cause of failure. As an example, the loads could be greater than what was expected in service. I'll give an example later on that explains when this could have happened. There's also subtleties that may not have been accounted for in the design process. And you may have missed critical failure modes that should have been accounted for in the design of these structures. And so it's very important that when you're designing these structures, that all the potential failure modes are evaluated and they're assessed to ensure robustness of the design to the loading environments it will experience. We also have situations where the root cause is not clearly defined. These are scenarios where you could have multiple contributors to that failure, but it's not possible to quickly determine, or it may not be possible to determine the one possible source of failure very accurately. Carelessness, as an example of that, is units matter. The Mars Climate Orbiter went off course because the prime contractor had provided the navigation team with operating data in the US imperial units rather than the specified SI units. I reference you to this Wikipedia article that goes into those details. But that's an example of not paying attention to what is being done. So units do matter, especially when you're working with a multidisciplinary team of engineers. It's extremely important to make sure that the units are consistent from one area of expertise to another. As an example, if the temperatures in one unit, in one area of expertise, are in the thermal area of expertise, are given in Kelvin, and your analysis that counts for the effects of thermal environments via the coefficient of thermal expansion, you better have those coefficient of thermal expansion in units that are compatible with another area expertise. In this case is Kelvin. That's an example of ensuring that units are consistent across. That's where hand calculations and checks and coherence checks are important to ensure that we're not missing something crucial. Here's an example of units in the force, length, area, and stress. In the metric units, you have 1 Newton as a fundamental quantity of force. The corresponding quantity in English units is a pound force. And 1 Newton actually tends to be will be equal to 0.225 pound force. 1 meter is a fundamental unit of length in the metric system. Likewise, this quantity is equal to 39.4 inches in the English units. For the units of area, 1 meter squared is a fundamental quantity for area, and you can then find the corresponding quantity in the English units, and so forth. And so what I want to make sure is that when you're working on the design of a structure, that we're trying to be consistent in that model. For example, if the forces are applied in Newton, you don't want to have in the same model units of inches. You want to make sure that you have a consistent basis for the units so errors are not made. And more importantly, you want to make sure that hand calculations are performed to ensure that there are no errors in the analysis. Underestimating environments have occurred quite significantly. The bridge midsection crashing into the waters of the Tacoma Narrows, November 7, 1940s, is an example of that. You have examples where, in this case, the structure collapsed due to the winds, producing an elastic flutter matching the natural frequency of the bridge. So, if you have a resonant condition, in this case, the amplifications of the deformations could be quite significant to the point that damage can occur. And so these actually help boost the designs in all future long-span bridges. In aircraft design, flutter actually is one of the design drivers. We want to make sure that flutter does not occur in aircraft design, as an example. And so it's important to ensure that the fundamental frequencies of the loading conditions, the loading condition forcing frequencies, do not line up with the natural frequencies of the structures. Otherwise, you could have a resonant condition that increases the loads quite significantly. So why study the theory of elasticity? Under applied forces, you're going to have the solid undergo deformations that will then develop internal forces. When you apply forces to a structure, internal forces are generated inside a structure that need to be studied. In an aerospace design under maximum expected loads, the idea is to ensure that the internal stresses inside a structure that are reacting the expected loads applied to the structure are under the material strength. Otherwise, failure could occur. And so for that reason, we have to introduce the concepts of stress, strain, and constitutive relationships so that we can then understand the concepts of the internal forces that are reacting to external forces. So the outline of today's lecture is external loads and boundary conditions, relating the external loads to internal loads, The stresses, which are internal forces that resist the external loads and must be in equilibrium. Strains that must, basically strains are deformations that can be measured, and the structure will experience the strains under applied loads. The stresses can be connected to strains through a constitutive relationship, which can be determined through measuring material properties, and we'll go through that. The finite element models can be used to solve this complicated set of equations we'll be discussing later today. So again, we'll be covering the types of loads we can have. We're going to try to find out a way of relating these external loads to internal loads, because external loads are physical quantities they can apply to the structure, while internal quantities to the structure are less obvious on how to define them. Stresses and strains are quantities that are measured on the structure and they're inside the structure, and then we can then connect the stress and strain relationships to then develop the equations that need to be solved either by hand calculations or using the finite element models, which is a numerical technique to solving partial differential equations. Here's an example of two basic types of external forces acting on a body. You say you have a body of material, a volume of material that has a shape. The weight is a type of body force, as an example. Electromagnetic forces can be another type of body forces. Anytime you have forces acting at every point in the volume, that is a body force. Inertial loads are another type of body force. You could also have surface tractions acting on the surface of the structure. A surface traction in an aerospace application will be the lifting conditions. You have pressure that's acting on the surfaces of the wing, and this differential pressure across the wing is what causes the lift. The fuselage itself will have a weight, that's a type of body force. The wing has a mass, that will have a body force, as an example. But surface tractions are forces that are acting on the surface. If you think about it, there's no possible way you can apply a force inside the body other than body forces. You can only apply surface conditions, surface loads on the structure. Point loads are actually not even possible. But we can represent point loads by applying a small traction on a very small area that will be equivalent to applying a surface traction. A surface traction can be perpendicular to the surface, but can also be tangential to the surface. When you have the tractions applies tangential to the surface, an example of that could be friction, as an example. Displacements are specified on part of the surface in some cases, and those represent boundary conditions. If I specify these deflections in the surface, then I am fixing those deflections, and so now I have a kinematic, we call it kinematic boundary conditions. And in this case, the fuselage could serve as a boundary condition to this wing, and the wing is basically fixed to that fuselage. And in this case, this condition here is a displacement boundary condition that has been applied. We can then apply loads to the structure on the surface, and that's also a kind of boundary condition. And this loading applied here, anywhere that loading is applied, you can't really apply a deflection boundary condition. For example, in this fixed wing that's completely fixed, I cannot apply a load there because that deflection that has been fixed, what it does, it reacts the external loads that have been applied on the surface. So you can either apply deflections or loads at a particular point of the structure. Applied loads and boundary conditions are, for example, in this case, I'm applying a variety of loads. And I said before, they can't quite apply point loads and moments to a 3D structure. You can do that by the application of small surface tractions applied to small areas that can then be representative of these forces, point forces. So there are ways to get around that in 3D structures. You could have a displacement constraint, for example, in this case. But the idea here and the goal here is to design aerospace structures such that the structure does not exhibit failure when it's subjected to the applied loads and boundary conditions. So that's what we want to do. We want to make sure the structure will not fail when I apply these loads externally, and it has these boundary conditions in place. Now, there are applications where you may not have boundary conditions that are deflections, for example. An airplane is an example of that, and it's one of the few applications where no physical boundary conditions are applied. For example, a bridge has very clearly boundary conditions on either side of the bridge. And they're kinematic boundary conditions because you specify deflections. An airplane that's flying in the air, does not have physical boundary conditions that are fixing the airplane in the air. But yet the airplane is flying and is in equilibrium because the forces applied to the structure are getting balanced correctly by the inertial loads of the structure. So what we want to do is to determine internal loads resisting the external loads. But to do this, we have to find a way of relating these external traction loads to internal loads adjacent to the surface of the body. Somehow these external loads have to be related to internal quantities that we can do something with. Here's an example of applied loads and boundary conditions. Here I have body forces applied to this cantilever beam, and the left edge has been fixed. We call this a cantilever beam under self-weight loading. You also have the example of surface forces being applied on this bar. And on either side, these surface forces are applied. And if I look at the internal forces, they're getting reacted by internal loads. So I have sectioned this beam to look inside and to see what's going on. And you're going to have these loads that are basically balancing the external loads applied. But let's see how we can relate those external forces to internal forces in the body. If I have a body of material and I apply a load, external loads to that material. So in this case, it could be a wing, or it could be a spacecraft or launch vehicle. I could section that body and then look at what's going on inside. My expectation is that internal forces will react to external forces per third Newton's law. For every force, there's a reaction in the opposite direction. And so we want to really examine that and see if we can apply some of those concepts, some of those fundamental concepts here. When I section that body of material and I were to look at a small area here, delta area, I will expect a delta force F, which is a vector that has a magnitude and direction that's acting on that delta area. I will expect that. And that surface area is going to have a normal that defines that surface orientation. If I take that delta force and divide it by delta area, and I take the limit as delta A goes to 0, I'm going to call that a traction quantity that's going to have units of PSI, or force per unit length. That traction quantity is of importance in this case, and I'm going to consider this to be a stress vector. This stress vector is the intensity of that force in that small surface area that we're considering, that has that normal vector n. On the right-hand side, I'm providing a different view of the same problem. I have a body of material, I do a sectioning here, and I expect that when forces are applied to this external load, that there'll be a force acting on a small area, delta A, that has a normal V in this case. So I'm showing two different conventions to the same problem to drive home what is going on. As I take the delta area to 0, my expectation is that the delta F divided by delta A, as the limit goes from delta A to 0, that this quantity is going to be called a traction vector or stress vector. And it represents the force per unit area acting at a point on a surface A where V, this vector V, is normal, is a unit normal at that point A, at this point here. The traction vector is going to depend on the position. I expect this traction vector to change as I move around, because if I go and study in this example, the example here is the body forces, I'll have expected the highest internal loads to be towards the surface of the material, not in the neutral axis. In the wing example, I expect the highest traction forces inside the body to be greater here towards the root compared to towards the wingtip. And so I hope that's clear that I'll expect higher traction forces here than here. Therefore, the traction quantities that we're discussing right now can vary as a function of the location of the structure. So again, I have external loads applied, getting reacted by internal loads in the structure, and I'm calling those a traction vector, which is units of force per unit length. If I were to apply structural loads to a body of material, it has body forces, which are forces that are acting at every point in the volume of the material, like gravity. Gravity acts at every point inside the material, and then I have traction forces applied on the surface of the material. I also may have accelerations acting on this body of material. The bottom line is these are external quantities that are applied. I have boundary conditions, they're physical quantities where deflections have been specified. And given these physical quantities are acting on this structure, I want to know what's going on inside the structure, because that's the quantity that's going to tell me where failure is going to occur. And those are the areas I want to reinforce. Those are the areas I want to make sure I have robustness. So one approach is to extract a cube, a representative cube that's inside the structure. And when I extract the cube out, I'm going to look at a Cartesian coordinate system here for a second. So I'm going to say it has x1, x2, and x3 is the coordinate system. We could use x, y, and z like I have here. I have elected to show both conventions, so it's clear to you that we're going to go back and forth in these conventions in this course. X typically will be 1, y will be x2, and z will be x3. And when I extract that cube out, what I realize is that this surface at the top, you're going to have 6 faces in this cube. I think you will agree with that. So pause the video and see if you can see the 6 faces in this cube. Congratulations, you did a great job there. So let's look now at what's going on with this face. This face is from the inside of the structure, and I expect a traction force like this one, this traction force acting arbitrarily on this face. I also have another traction force acting on this face, another traction force acting on this face. I have traction forces acting on 6 of these faces, and when I look at that traction force, I can decompose that traction force into 3 different directions. So a vector can be decomposed into 3 different directions. In the x1 direction, the x2 direction, and the x3 direction. So that traction vector quantity can be decomposed into tau 3.1, tau 3.2, tau 3.3. And on this face, it can be decomposed into tau 2.1, tau 2.2, tau 2.3. And I'm calling these stress quantities that are components of that traction vector on this face. Remember what we've done, we have excised a cube from inside of the structure to understand how these forces are reacting the external loads applied. And I'm calling these force quantities stresses. And on each of these faces, there's a stress vector T, I've called T here, T bold, or T traction vector there. And that traction vector can be decomposed into these 3 components. When I look at phase 1, you're going to see here 2 indices. Let me go through that. The first index is 1, and it represents the phase on which those tractions are being discussed. So these stress quantities here, tau 1.1, tau 1.3, and tau 1.2, and we're going to use sigma as well in this class. Tau and sigma are stress quantities, and we're going to interchangeably use them. 1 is a phase on which that traction vector is acting, and the second index corresponds to the direction it's acting. In this case, 1 is the 1 phase, so that makes sense. And then I have 1, the second index, 1 shows the direction that traction, that stress is acting on, and the direction. Here I have tau 1.3 because tau 1.3 on this phase, this traction vector, this component of that traction vector is acting on the number 1 phase, so that's what that 1 is, on the 3 direction. So that's why it's called tau 1.3. And then tau 1.2 is because I have the traction vector looked at on phase number 1, which is defined by x1, and is acting in the 2 direction. So I have 3 components of stress here, 3 components of stress here, 3 components of stress here, and I also have another 9 components that are hidden in this cube. I have a total of 18 components in this cube. The important thing to understand here is that these are just stress components that correspond to that traction vector we just talked about, that has units of pound per pound or forces per unit area. And these stresses are the ones that are reacting to external forces. And my goal is to determine these stresses, because these stresses are going to tell me when the structure fails. And it helps me then design a structure so that we can make it robust to the loading that we will experience in service. There's a total of 18 components of stress, but really 9 of them are independent. If you think about it, a traction vector applied on this surface must be equal and opposite sign to the traction vector on the opposite surface. And the reason is because of Newton's third law. So therefore, tau 3,3, if it's oriented this way, must be equal and opposite in the opposite phase. And tau 3,2, which is acting on the two direction like that, in the opposite phase, it will be of equal magnitude, but pointed in the -2 direction, in that bottom phase that we cannot see, x3. Tau 3,1, which is positive in the top phase, should be in the equal and opposite direction in the bottom phase. So I really have all these components are the same in magnitude in the opposite phase, but they're in the opposite direction because of Newton's third law. So I hope that's clear on what we're trying to accomplish. Let's look at the stress components now. So these are the traction vectors we talked about, and I don't want you to lose sight. What we've done is we excised this cube from this structure. You know, I could have excised the cube from this wing or this fuselage, and then look at what is a cube look like and what is going on. So we discussed there's a traction applied here, a traction applied here, a traction applied here, not applied here, but they're reacted. These tractions are reacting external loads applied at a particular point in the material. Now what I'd like to show you here is the very thing I talked about. I talked about this traction vector in the y phase, and I changed the coordinate system on purpose. Here's x3, but it doesn't matter. It just follows the right-hand rule, x, y, and z. And the point here is this traction vector on this y phase, and I put this y bold on the top here to delineate that this phase is the y phase, that this traction vector can be decomposed into these 3 different quantities. And here I'm showing you those 3 quantities. We can use a Cartesian system to represent T bold, and here this traction vector can be represented as sigma yx. Sigma yx is this direction here, and is I hat because it's in the x direction, is the x component, plus sigma yy, which is this component here, and that's in the y direction, so that's j hat, plus sigma yz, which is in this direction z, and that makes sense, that is k hat. So this traction vector has been decomposed successfully into the 3 different stress components that have units of force per unit area. I can also do the same thing with this phase here, this traction vector here, and this traction vector here. So it does make sense. If I were to excise a cube out of this structure, I expect 6 tractions extracted out of these phases. And they're reacting these external loads, and they are very independent upon where you are in the structure. I can now take these 18 components of stress, which I discussed now, there's only 9 components of stress, because on the opposite phase, the magnitudes will be equal, but the direction will be opposite. So I can put these stress components into a matrix notation here, as you can see. And I'll put, by convention, I'm going to put sigma xx, sigma yy, and sigma cz in the diagonal terms. And sigma xx and sigma yy and sigma zz are the stress quantities that cause the cube to expand in all directions. We also then have, and they're the normal stress quantities. We also have the off-diagonal terms, tau sigma xy or tau xy, tau xz, and tau yz. These are the shear stress components that cause the cube to distort, and these quantities here are the ones that are tangential to the surface, as you can see here. These shear stresses cause the cube to distort, while the stress components in the diagonal term cause the cube to expand in all three directions or contract. So these are the 9 components of stress. Note that this cube here really represents a material point in the structure. So in other words, this is a point, but where it represents a cube to understand how the stresses are acting on that point. What I can look at now is what are the traction force at an arbitrary plane, at a plane other than the straight faces that we see here. They're defined by each of these coordinate systems. So what I can do then, I can then define what plane I'm interested. Let's say I'm interested in a plane n hat. So this plane n has a normal which is defined by nx I hat plus ny j hat plus nz k hat. And the goal then is to determine what is the traction on that plane at that particular point, material point. So what I want to do, I know the tractions. So what I have to do is take the traction vector and take the dot product against n to then enable us to find the value of that traction on that face, which is then going to be sigma xx times nx plus sigma xy times ny, and then I will have sigma xz times nz. And so that's going to give me the component of that traction in the x direction on that plane defined by this normal, which is a unit vector n. And so then I can do the same thing. I can take t bold y and find the dot product of ty bold dot n, and that's going to give me the projection of this vector on n, and I'm able to then find the traction in the y direction that's acting on that face, and that face is defined by this normal vector n, which is a unit vector. I can then repeat the process with the traction vector t bold. And note, these traction vectors are the ones that are acting on these faces. What I really have when I calculate everything is I can put this relationship into this format. Tx, ty, and tz is a vector, and then I have a matrix, which is, these have been put into the matrix like that. And just to really understand what this looks like, this convention is matrix notation. And it's nothing more than 3 equations that have been written in a compact manner. Instead of writing the equations one by one, we can just put them in the matrix format, and that's just 3 equations that we got here. When I look at this, sigma xx times nx plus tau xy times ny plus tau xz times nz equals tx is the first equation. So the way the matrix notation works is that you take this component and multiply by nx plus this component multiplied by that component plus this component times this component. So this row is multiplied by this column correspondingly term by term and then added together. That's going to be equal to ty, adding those things together. So that's what we got here. That's how you read this. And this is the first equation, second equation, and third equation. This relationship is extremely important and will be used later, and I'll show you how. But I want to give you an example from the book. And again, I really encourage you to get hold of the book because we're going to be using it heavily during this course. Please contact me here at the email at the bottom if interested in the book. The state of stress in a cube inside the body is given by this. So I have a state of stress that looks like this. I want to find the tractions on this ABC plane. So I want to know what is the traction on this ABC plane. So take an example of a structure that has been subjected by loads, and now I know the state of stress. I calculated somehow the state of stress inside the body at this particular point, and it's given by this. Now to remind you, 40, 50, and 40, 40 is sigma xx, and 50 sigma yy, and 40 sigma zz. These three components of stress are the ones that act to stretch the cube in three directions, in the normal directions. The off-diagonal terms, 40, 0, minus 60, these are the shear stresses, and they act to cause a cube to distort. So very important to understand that right now. And so how I'm going to use a relationship, my strategy to find a traction vector acting on this face ABC is to use this relationship, actually called Cauchy's relationship in the book. You will see that. So what do I need? I have this completely defined. All I need to find is this normal unit vector. That normal unit vector can be quickly determined because I know this distance, I know this distance, I know this distance. And to find a normal vector to this face, you can use the area approach. I'll walk you through that really quickly here. So the first step is to find the area of each of these triangles here. For example, I have AOC, AOB, and BOC. So we can find those fairly quickly. The area here in this case is given to us. So it's not given to us, but the dimensions of point A, B, and C are given to us relative to O. So I can determine the area. So the first one I want to find is the area corresponding to the x direction. This face right here, AOB, is the one that corresponds to the x direction. Note that I have 40 as sigma xx, correctly so, on that face AOB. I'm drawing that so you can see what that looks like on the opposite face. I also have a shear load of 40, which is sigma xy. That makes sense. It's in the x phase, in the y direction, and it's pointed downwards because it's in the opposite phase to x. And we talked about that third Newton's law. So that makes total sense. This area right here is just a right triangle, so that's just 1/2 delta times 3 delta, which is 3/2 delta squared. And I put I hat because that's the area corresponding to the x direction. Then I will look at the area corresponding to the y direction. That area here is given here by the triangle BOC. And here, that area is 3 delta times 2 delta divided by 2. So this length times that length divided by 2. And that's 6 delta squared divided by 2. Then that's why I have 3 delta squared here. I also have drawn here the force, the traction forces on the bottom face. And I'm going to talk to you through that. So this is 50. Right, that on that face is 50, and that corresponds to sigma yy, rightfully so, because we talked about this being sigma yy, so that's on the y face, and it's acting in the opposite direction because we're looking at the opposite face. Then I have 40 also again, sigma yx in this case, and sigma y case, y, because it's in the y face, acting in the x direction, but the opposite direction because I'm looking at the opposite face of the y face. And then finally, I have minus 60, which is minus 60 on the top face of y. And so when I look here now, that's yz, so the y face in the z direction, but it'll be pointed in the z direction in the top face. In the opposite direction becomes in this direction. So I invite you to take time. In the book, we go through that example very carefully. So I want you to look at that on how to draw these things in here. But the bottom line is I'm able to find the area for this triangle, and now I have to find the area for this triangle. The area for that triangle is delta times 2 delta, and that's going to be delta times 2 delta divided by 2. That's delta squared. So now that I have found the areas for these little triangles, I can now find the magnitude of this area vector. And that's easily found as 7 over 2 delta squared. And I'll put that in the denominator. Delta square cancels out. And so I'm able to then find the normal vector n that defines the ABC plane. Because what I'm really interested in is, given the stress component on a point, I want to know what the traction forces are on this face. That's really the question that we're after here. So I want to point out the importance of ensuring that you understand how the stress components are drawn in this cube, partial cube, because we section that cube with a slice ABC. Normally this would be a cube. We sliced it with ABC, that plane. So I look at now at the stress component sigma ZZ, which is 40. So that's why it's pointed in that direction, and the magnitude is 40. And then I also have sigma ZY in the Z phase in the Y direction. That's this component here, and that's 60 as well. So I'm ready now. I have the stress components provided to us by the problem statement, and I have calculated n, and so all I have to do is execute that multiplication. So this row times this column gives me the first number here. This row times this column gives me this number here. So 40 times 3/7 plus 50 times 6/7 plus 40 times 2/7. And that'll give me this number here. So I have three components of the traction vector. And that's the traction vector now that can be drawn on this face ABC. So the relationship really allows us also to relate the applied tractions on the surfaces, just the stresses inside the body. So if I don't know how these traction forces relate to the stresses just inside the body, I can also use this relationship. Note that the stresses were defined in the Cartesian coordinate system XYZ, and so it is convenient to take that traction which is applied on a phase that may not be aligned with XYZ. We can use that normal to define what those stresses will look like by using this the so-called Cauchy's relationship as described in our book. So why do I need to do that conversion? And the reason is very simple. I'm applying tractions to the body of material, accelerations and body forces. But me applying pressure loads and things like that, that's not sufficient. I need to figure out when the body is going to fail, and for me to do that, I need to somehow relate these traction forces to stresses just inside the body, the cube just adjacent to these traction forces. So I can use these Cauchy's relationships for multiple reasons. One is to relate the tractions outside the body to the material point just inside the body, to these stress quantities. But I can also use them to determine the tractions at an oblique plane that may not align with X, Y, and Z at a material point inside the body. And why we need to do this is because we need to determine at which the stresses inside the body that will produce failure of the structure. So this relationship, creating this relationship, is extremely important. So let's see how we can use this Cauchy's relationship information. Let me remind you what we're trying to accomplish. What we're trying to do is to relate traction forces outside of the body and determine the reaction forces inside the body that react in these applied forces, these acceleration forces, body forces. What we want to determine is where's the greatest stress inside the body, which is the reaction force inside the body that's reacting these external loads, and then determine whether the highest stresses are below the strength of the material. That's really what we're trying to accomplish. But to get there, the first step is to relate these traction forces applied to stresses just adjacent to the surface. And to do that, you can also use Cauchy's relationship. Note that when traction forces are applied, they may not be aligned with the Cartesian coordinate system, while the stress components were aligned and defined with the Cartesian coordinate system, X, Y, and Z. And so that's how you can also use this information. If I know the tractions and I know the normal vector to that surface, there has to be a combination of stresses that make that happen. And that information is important because those stresses then get transmitted out throughout the structure, and we can then determine where the highest stresses are in the structure. So that's what we want to do with Cauchy's relationship. And then the other reason to use Cauchy's relationship that may come up is if I want to find out in this cube, in this material point that's represented by this cube, I want to find a traction vector at a plane that's not aligned with X, Y, and Z. So that's another reason why that can be beneficial. So I want to answer the question of at what orientation this cube needs to be so that the stresses on each face that we have, basically only normal stresses are acting. There has to be one. For example, when what I'm really trying to do, right, I want to take and find which plane ABC. So say you don't know these dimensions. These dimensions are not known. This delta, 3 delta, 2 delta are not known. I want to know which plane slices through a cube in such a manner that on that face only a normal traction is acting on it. There's no shear stresses. That becomes very beneficial for predicting failure as well. And so that's why I want to cover that. So that question is really what vector n gives me a traction vector that's aligned with a normal vector. That's really the question. What normal vector n will give me a traction vector t such that that traction vector t is aligned with n? Because if that's the case, then the traction vector on this face is normal to that surface only, and there's no shear stresses applied. So that's what we're trying to do, and that's what we want to accomplish with that question. So let me walk you through that thought and how we can get. So what I want to do is I want to find the plane ABC such that only normal stresses are acting on that plane. So if I defined a normal to that surface, ABC, and I slice ABC through a cube, I shouldn't have any shear stresses on that surface. Basically, no tangential tractions to this surface, only normal to that. So if that's the case, traction T has to be proportional to N via this relationship. And so therefore T hat must be equal to some value lambda, which is a number, times N hat. And T hat is aligned that way with N hat, has to be. It's only scaled by lambda because N is a unit vector. And so if I expand this, I get lambda times N1, lambda times N2, and lambda M times N3. That's the vector that T hat is. But I also have Cauchy's relationship, which states that sigma xx, sigma xy, sigma xz times N1 times N2 times N3 gives me the first component. In this case, is lambda N1. So I can multiply all this stuff out, but this is Cauchy's relationship. And this is equal to the right-hand side here. So this is equal to that. Remember, this relationship here allows us to relate the tractions at a plane that's not aligned with the Cartesian system to the straight state that's described on a cube, right? So this is what this is giving us. And so this has to be equal to this relationship. And I know the stress state is given to us. I don't know the N. I don't know this vector N or lambda that produces an oblique surface or plane that slices through the cube such that no shear stresses are existent in that surface, only normal stress. And so I can put this equation here, this vector into this format, which is lambda, lambda, lambda in the diagonals, times this vector N1, N2, and N3. So this row and this column obviously gives you this number. This row and this column gives you this number, and so forth. So this is clearly equal to this right here, and so all I have to do is equate this to that, or bring this to the other side of the equation, and when I do that, I get sigma xx minus lambda, sigma yy minus lambda, and sigma zz minus lambda, where lambda is the only thing that's unknown along with the vector n. We don't know the orientation of that normal that gives us this traction vector t, so that's only the normal component that exists. And so moving forward then, what I want to do then, and again I showed it here if you want to pause the video and see how I did it with equations, but I get the same answer. And the thing is that N1, N2, and N3 cannot be 0. So we know that N1, N2, and N3 cannot be 0 because I will never be able to define a surface whose normal is 0, 0, 0. I have to have a non-zero unit vector that works. And so therefore, this matrix, the determinant of this matrix has to be equal to 0. Okay? And you can do this in MATLAB. You can find the determinant. When you find the determinant, you'll find a characteristic equation as a function of this lambda that's unknown. And once you do that, I1, I2, and I3 will be numbers also, because they'll depend only on sigma x, tau x, y, all this stress state that's fully known. So once you know that, you can then calculate lambda, and once you know lambda, you can plug it back in here, and once you find lambda, this matrix is fully populated. And all you have to find now is a vector N1, N2, N3 that has components N1, N2, and N3 that's a unit vector, such that this relationship holds. And so that can be done by Mathematica or MATLAB or through online sources like wolframalpha.com. And the idea here is that you can now calculate the principal stresses and associated planes at which that happens. So I hope that's clear. It's fairly simple. Here's an example. I have a stress state of this kind, and so all I have to do is use this equation right here, find the determinant of this equation, and when I do that using Mathematica, I find this equation, and then I can just find the roots fairly simply. When I find the roots, I find it's 4, 1, and minus 2. It's a cubic root, so I should get 3 principal stresses, and for each principal stress, I can plug it in here, back, and then calculate the vector that will make this equal to 0. And that entails solving this system of equations, knowing that I also have a unit vector. And so when I do that, once I do that, I find the eigenvector, or the normal plane, n, The plane whose normal, the traction on that plane only has a normal stress. And that normal stress is 4 in this case, and the normal vector n is this in this case. You can then, in a similar fashion, find the other two roots, which are the principal stresses and the associated normals. And this is useful for design of structures, because some failure criteria may use principal stresses as a criterion for failure. Let's now move to equilibrium equations. So we know from second Newton's law that the summation of forces, the net summation of forces on a particle equals the mass times the acceleration vector. And so we're going to use this relationship today for the body of material that we've been discussing. So this is the body. It could be an airplane, aircraft, spacecraft, launch vehicle. And there's tractions applied on the surface. There's accelerations applied to the body, and potentially gravity or some other electromagnetic force. And our goal, to remind you, is to find the stress inside the body that is reacting the external loads. And these stresses will then be compared to the strength of the material to predict failure. That's the goal that we have in mind in the elasticity of 3D bodies. And so I want to draw your attention to second Newton's law, but in the integral form. In the book, we do it differently, but here I'm showing you a different way of tackling this problem. So since the body force is per unit volume, I can take the body force per every piece of volume and add them all up, and that's why I have this integral. And it has a vector because the force always has a vector. It has a magnitude and direction, and in this case the body force could have a direction. And it's times dV because the force acts per unit volume. So gravity is an example of that. Gravity acts on every point of the material, and it is a body force. Then I have the traction forces. It could be pressure, lift, drag, or some quantity per unit area that's applied on the surface of the structure, and that's integrated over that area where the forces are applied. So this right here is units of force, and these units of force. Now, these units of force has to be equal to AMA. And so I have the density times acceleration. Now the acceleration is acting every point in the volume, and if the acceleration is applied uniformly and the density is uniform, then you get AMA, the mass times acceleration. In this case, density could vary, so we'll just keep it general for now. But the bottom line is that we have here an integral form of the equations you may have learned back in physics. The important point here and the distinction is that I'm using the integral form because I'm looking at a deformable body. That's why. So represented in this equation are really three equations. Summation of forces in the x direction, summation of forces in the y direction, and summation of forces in the z direction. Note how Bx, By, and Bz are the components of the body force B hat. Tx, Ty, and Tz are the components of the tractions applied on the surface, and they're applied on a particular area of the surface. And then I have the acceleration terms as well, Ax, Ay, and Az. So I have three equations, just like in physics, where we had summation of forces in the x direction, y direction, and I didn't put here the z direction, but you should also do that one if the behavior is in three directions. And so now that I have these three equations, the question is, so what? I have the tractions applied, I have the body forces applied, at the acceleration supply. But that doesn't help me determine when the structure breaks. So I have to now somehow tackle this problem. And one area where I can examine carefully is distraction force T. Distraction force T can be related to stresses inside the body. Now I'll pause the video to see if you can remember how to relate tractions to stresses. And I hope you got it right, because to do that we use Cauchy's relationship. If you recall, in Cauchy's relationship, we relate the tractions to stresses using this normal quantity. So I can then expand on that and use it. I can relate that traction to stresses inside the body, and the normal here local is n. And so I'll have sigma xx nx plus sigma xy ny, sigma z nz for tx. That's what I've substituted for. So I have used Cauchy's relationship for that. I'll do the same thing for ty and tz. And I'm able to do that quite successfully, as you can see here. And now the next step is so what again, because this is a volume quantity, this is a volume quantity, and this is a surface integral. So this integral is only on the surface, and stress is something I want to be able to tell as a point-wise quantity. Right now, this is only on the surface, but I really want to relate it to stuff going on inside the body, because that's where the body could fail. And so to do that, I have to use the divergence theorem. Now, you may not recall it, but from calculus, we can relate an integral on the surface to a volume integral. And that's simply to convert that surface integral to volume integral, all you have to do is remove this unit normal and then convert that to a derivative. And this nx becomes derivative with respect to x, ny becomes derivative with respect to y, and the nz becomes a derivative with respect to z. And the point now being is that this is a volume integral, while this was a surface integral. So I'm slowly starting to connect a surface quantity to a volumetric quantity, something I can then go in and determine whether stresses could be a problem inside the body. And that's really the goal here. And it is a mathematical miracle. Think about it. We're able to relate a quantity that's a gradient of stress, and we're able to relate that to stuff happening inside the body, to stuff happening on the surface of the body. And that's an amazing relationship that allows us to do this. Now that I have everything in volume quantity, I can now realize that this is true for every point in the volume of the body. And so I can then bring everything to the left side of the equation and put it all in a single volume quantity. And what I find is that the integrals are not necessary for this relationship to hold, because this holds for every point in the body. So bx plus this quantity must be equal to rho ax. And I'm missing a row here, and I apologize for that, but this is true for every material in the body. And so now Bx plus this quantity plus a, and it must, so we must have, if this is true for every point on the volume, we must have that the integrand must hold true, that equality. So therefore we find these three equations of elasticity. These are the equilibrium equations of elasticity. These equations have to hold true given the body forces and accelerations and density of the body. These stress quantities have to hold true. Now let's take an example of a situation where no body forces exist, no accelerations exist. In this example, the stress is equal to this, and all I have to find now whether the system is in equilibrium. So I'll just use the equations that are given. I have no z's, so that's why I did not include this third column here, because it's not necessary. But when I take the derivatives, you can see everything checks out. And so this stress state inside the body of material is in equilibrium, and it's a solution to the problem for a given loading condition. Another consideration that needs to be looked at is the conservation of angular momentum. So we looked at the stress is in equilibrium, but what about the conservation of angular momentum? If I take the body of material and draw an arrow vector r to that body of material and do a cross product against B, the body force B, and r cross t, so I take r cross t, and then I also take r cross acceleration of the body. This will then give us a moment calculation. If you recall from statics and physics, r cross a force gives me a moment. So I'm actually doing a summation of this r cross body force, which is per unit volume. So I have a bunch of unit volumes, and the body force is applied to each of these unit volume material, and I'm incrementally adding them all up, which is the reason I have that integral. And the same thing with the traction forces. I have traction forces here, and r cross a small portion of that traction forces, just adding them all up will then be equal to this quantity here. And so all I've done is taken this relationship here and done r cross to the top row. It is very tedious to prove, but once you go through this calculation, you actually find that sigma xy must be equal to sigma yx. And that sigma xz must be equal to sigma zx, and that sigma yz must be equal to sigma zy. And so, in fact, the stress tensor is symmetric, and while before we said there's 9 components of stress, only 6 of them are independent because of the symmetry conditions that are caused by the angular momentum relationship. Let me show you how to do this in a simpler way. In the book, we also have it done differently. But one way to do this is to consider a box of material. And say I just have shear stresses. Sigma xy, sigma xy. We know that this stress must be on the x face because that's the first index there. And the y here is in the direction that it's acting on. We also know that this must be the same in magnitude as this one, but opposite direction because of third Newton's law. I also have sigma yx in this face because that's the y face and is acting in the x direction. I also have sigma yx in the bottom face in the opposite direction. We don't know if sigma xy and sigma yx are equal, but we could see if that is the case by summing moments about the center. And so if I have a cube, or if this length is A and the depth was A, then the force contribution due to this stress is sigma yx times the area, which is A squared. And so I've converted all these stress quantities into forces, and I have done a simple summation of moments about the center. Sigma xy, for example, times a squared times this distance a half gives me the contribution moment due to this for a stress applied. And I can repeat it for the other quantities. And when I'm done, what I find is that a cubed cancels out, divided by 2, and I'm left with sigma yx equals sigma xy. So we had 9 components of stress earlier that were discussed. And these 9 components of stress, what we're saying is that these diagonal terms must be equal. Going back to the cube, what we're saying is that this tau zx must be equal to tau xz. And then this tau yx must be equal to tau xy. And so forth. Tau yz must be equal to tau zy. So I hope that makes sense. So let's discuss strains now. We went through stresses, and stresses are basically reaction forces inside the body reacting to external loads applied that could be accelerations, body forces, traction forces such as aerodynamic forces from liftoff or during flight. So what is strain? We're going to go into strain now. A structure deforms as loads are applied. I think we know that the relative deflection of the material is how we try to define strain, and they tend to be materially and directionally dependent. The deformation is going to produce changes in the body of the material, the dimensions of the body of the material. It can change its shape. The deformations induce strains throughout the structure, and strains can be measured typically using strain gauges and digital image correlation. Strains can be measured directly in a variety of ways, and deformation patterns for solids and deflection shapes can be easily visualized when you apply a load. By contrast, when you look at the stresses are internal quantities to the structure and can really only be determined through indirect measurements of forces or by numerical simulations. So strain and deformations are physical quantities, are tangible, are clear. You apply a load to a diving board, you can see the diving board deflect. But stress, not so much. But strain plays a critical role because when you apply loads, strains do develop, and it is important to understand what is going on with the structure, and deformations can help you gain that understanding. Here's an example of an aircraft subjected to cyclic loading, and this loading that's been applied is to verify the behavior of the wing to ensure is adequately qualified. You can see here that there's a number of load cells that are being used to pull the wing. And this wing is going to deform 20 to 35 feet or more. But the idea here is to demonstrate that the wing can take the loading conditions in flight. As you can see here, the load cells are attached to the wing. You can see the wingtip deforms or deflects a lot. But just because the wing deflects a lot, it does not mean that that's where it's going to break. Because you can have large deflections, yet the strains in that local area could be lower. In fact, very likely the highest strains are towards the root of this wing, as that must carry the highest bending moment. So I'll move here to rigid body rotation. You could have rigid body rotation as an example. You can have rigid body translation. And in these two cases, no strains are developed. But in general, you're going to have stretching and distortion, and these do cause strains. Here's an example of distortion. of the body, and distortion of this body was originally square. That's going to cause strains. And now I can rotate this distorted image or the structure, and I can translate it, and this rotation and translation will not cause additional strains. So it's really important to understand that the strain and is a quantity that's useful because it's going to account for rigid body rotation and rigid body translation. And that's not going to affect how much it moves or deflects. It's not going to affect the real straining behavior of the part, which is a quantity that really matters because it's directly related to when failure could occur. Here's an example of deformations. I have an undeformed element and it went through rigid body rotation. No strain should have formed in this case. I could also have an undeformed element and apply a load and I get a horizontal extension. I can then also apply a vertical load in this direction and I'll get a vertical extension. I can apply distortion or shear, and this will then distort in this manner. So in general, you can get stretching of the material and distortion. We have here undeformed and deformed body. You can see here when I apply a load, you get a deformed body. Now this tip, the strains could be low, perhaps the strains are really high at the bottom. You have to do the calculation to really know where strains could be the highest. And just by looking at deflection alone may not tell you sufficient information to know where you may have the greatest problems. So let's consider an axially loaded beam or bar. Here I have a bar with a line that has been marked with a marker, AB. And this point A is located at distance x, and I'm going to say this point B is in the vicinity of point A by delta x. Now, clearly it's not the vicinity because it looks large, but I want you to pretend it is. I'm just zooming in so you can see what's going on with that line. Now, point A is going to go some deflection, an amount U. And point B is going to go an additional deflection, U plus delta U. And we know it's U because the line moved an amount U totally, but then also there's a stretch of that line. As you can see here, A prime, B prime, that distance looks longer than here. So that's where that U comes from. And so what is the strain at A? The strain at A is the deflection at UB, so this, how much this moved, minus UA. And so when I look at that, I get delta U divided by delta X. So U plus delta U minus U gives you delta U. And delta U divided by delta X gives you the strain at point A. Basically, if this is the undeformed length, this is the undeformed length, delta X, this is the change in length of that line divided by that original length. I'll take the limit as x goes to 0 since I want to look at the vicinity of A, right in the vicinity. And what you get is that the strain epsilon x equals du dx. If you have a uniformly loaded and distributed deformation over the original length L, or this whole thing, then you could have, you can measure the length L after the loading is applied, minus the original length without the load, divided by the original length, and you will get the strain that's basically an average strain over this whole bar. Shear strains can also be calculated. So you can look at here at a square ABCD. I've captured epsilon xx, which is derivative of u respect to x. I've demonstrated that. You can repeat the exercise in the y direction and z direction, and you're basically talking about stretching, right? This strain here clearly is related to stretching of this bar. In the y direction and z directions, you're going to have a very similar relationship that can be derived. And you also have to consider distortion. So these ones talk about stretching, but they don't talk about distortion. And so consider here a square ABCD. And a length here is dx, length here is dy. And I'm going to have, again, a deflection of point A to this point. And I'm going to say it deflects an amount u in x direction and an amount v in the y direction. This point then deflected more, and it deflected an amount u x plus dx comma y, because this distance x, this is dx, so clearly the coordinates of this point now that we're looking at is u x plus dx comma y. Now we have also the deflection of point C, and that point has moved an amount v, as you can see, but y plus dy. And so that's that point here. You can then determine these angles using geometry. And what you find here is that since this distance is u, and this distance here is u x plus dx y, you can calculate this length and this length, and what you end up getting is dv dx dx. And here you get du dy dy. I ask you to pause the video to see if you can get to that. But the bottom line is that distortional loads will cause, the shearing is going to cause distortion, and it's going to change the angle. And it started at 90 degrees, it changed angles, and the amount of change angle here is alpha, and the amount of change angle here is beta. So alpha plus beta is a total amount of angle change. And what you'll find is that it's going to be twice, so put the 2 on the other side of the equation, and the angle change is going to be twice epsilon xy equals the derivative of u respect to y, which is this coefficient here, plus dv dx, which is this coefficient here. And you can rarely get that, because if this is dx, then dv dx divided by dx gives you the tangent of alpha, and the tangent of alpha for small angular approximation is close to alpha. And so again, I kind of did it for you, but I want you to go ahead and do it for this one here as well. And you'll get that alpha plus beta will be du dy plus partial of v respect to x. And so that's a strain twice epsilon xy, which is going to be the angle change. And now I can repeat the exercise for the 2 other directions. And you also want to realize here, and you're going to find that the strain tensor is also symmetric. Not only I have the diagonal components that are related to stretching of the material, the off-diagonal components are related to shearing of the material. If I now determine the components of strain for the following displacement field, and let's assume A, B, and C are constants, and U is non-uniformly varies across X and Y, and V, the deflection V, varies across X and Y in this manner, and also W, then you can calculate the strains because of this deformation applied. So strain epsilon xx equals the derivative of u respect to x. In this case, you get A times z. The epsilon y is the derivative of v respect to y. So u is the deflection in the x direction. V is the deflection in the y direction. And W is the deflection in the z direction. So for this one, you get 2by. And here you get 0 because there's no z. So the derivative of W respect to z is 0. And you can calculate the rest of them fairly easily. The derivative of epsilon xy equals 1/2 derivative of u respect to y. And in this case, you have no y here, so that's 0. The derivative of v respect to x, which is, it does have an x, and so then you have 2bx. So that gives you a total of bx. So in reality, strain, the angle change is really 2bx. So twice epsilon xy. And then again, I have here epsilon yz, and I can repeat the exercise to calculate how much straining I have in the material. I can also calculate the principal strains and directions. And to do that, you can calculate the determinant just like we did before. You put this in a matrix, this matrix like that, and you put a minus lambda here, minus lambda here, minus lambda here, and find the determinant. You follow the same process we had before and calculate a characteristic equation. And based on that, you will then determine what's going on, what are the principal stresses, and the eigenvectors that represent that. Those, where those principal stresses are really, principal strains are really occurring. You also want to point out one thing here is that when you add these diagonal terms, they usually are related to the change in volume divided by original volume. So that's an interesting fact that's worth pointing out. In any event, there is a plane at which the strains are only acting normal to the cube. Stress and strain relationships. So the summary so far, we have 3 components of normal stress and 3 components of shear stress. The 3 normal stresses are the diagonal terms in the stress matrix. The shear stresses are the off-diagonal terms. The stress tensor is symmetric, and we found that through the conservation of angular momentum. We also showed how we can use Cauchy's formula that relates tractions at an oblique surface to internal stresses in the body. We also demonstrated that there's 3 equilibrium equations that govern the stresses in the body. We also have 6 strain-deflection relationships, which were discussed here. You can see them here on the left-hand side. And we need to somehow relate now stresses to strain to be able to proceed with trying to figure out a way of solving for these stresses that are really reacting the external loads being applied. And those stresses are going to help us determine whether structural failure could happen. So in linear elasticity, we must have 6 stress components of stress that are related to 6 components of strain. And so these stress components are connected to these 6 components of strain that can only happen through an empirical relationship that we can determine through testing in the labs. We call that the stiffness matrix 6x6, and it will relate stress to strain like this. And I know this looks like a lot of information, but now take that stress matrix and put it in a column like this, and the strain matrix we showed earlier and put it in a column like this. So this strain right here are the 6 strains we talked about. These are the 6 stresses we talked about. The first 3 on either side correspond to the normal quantities, while the bottom 3 are the off-diagonal quantities, and they correspond to the shear behavior of the structure. Due to material symmetry, we're going to just say that this is symmetric. we're also going to talk about a contrasted notation, which is used often. But first I want to show you the order where how these stresses are located and how these strains are located in this column. So usually it's convention to put the stress, the normal stress component first, and then this stress with the highest index, 2 and 3, or y and z. So note that I'm using 1x, 2 equals y, and 3z interchangeably. So sigma 1, 3 will be xz, and this will be xy. And the contracted notation, what it does, it just makes it easy to write down, but you should just use this format if you want. The same on this side. Now you'll see there's a twice here, and the reason is because twice a shear strain does have a meaning. That's the angle change that we talked about earlier. When you apply shear loading, you'll get an angle change from 90 degrees to some other angle, and the angle change is the shear strain, and that can be calculated. I'm also now showing you how this looks like when I use x, y, and z. Fairly simple. You can just replace 1 by x, 2 by y, and 3 by z, and then just replace it here. And it's another way to look at the data, but with different symbols. And you can feel free to pause the video and see how I did it there. If I want to find strain in terms of stress, I'll invert C to get it to the other side of the equation. And that's what I've shown here. This right here is strain equals a quantity times stress. This quantity can be found by inverting the C matrix. And in this case, S is called the compliance matrix, and is an easier quantity to measure directly from testing. And so we're going to focus on this quantity, and then I'll show you what C will look like once we calculate S. Because once we calculate S, we can find C. So the first step is to understand what is going on. So let's first consider a class of materials called orthotropic properties, orthotropic laminates. Those laminates will exhibit 3 planes of symmetry. And these 3D orthotropic plates behave interestingly. So when you apply normal stresses to a 3D orthotropic plate, and I'll draw a cube here to demonstrate. If I apply normal stresses to this cube, then no shear will occur by applying these normal stresses. And as a consequence, we have that sigma 1, 2, sigma 1, 3, and sigma 2, 3 is 0. Also, when I apply shearing, we're going to make the assumption that this material, when you apply shearing, that you don't develop shear. So say I'm applying shear in this plane, in the 1, 2 plane. Okay, so I'm applying shear in this plane. And so what we're saying is when I apply shear in this plane, such as this, no normal strains will develop because of that. And the shears in the other direction, due to applying this normal shear, this shear in the 1, 2 plane will not cause shear in the other 2 directions. So we know those will be 0. Okay. This angle change, which is gamma 1, 2, and measures the angle change from here to this angle change. So this angle change from this to that. That angle change is tau 1, 2 divided by G 1, 2, and you can measure it because Tau 2 is a loading condition that can be applied, and you can measure the shear strain. If you can measure the shear strain and you know how much loading you applied, you can calculate the shear modulus. This G is called the shear modulus, G12. I can then perform the experiment again in the 1-3 plane and then in the 2-3 plane. Torsion tends to be the test that's typically used to measure the shear modulus. So there's 3 different shear modulus for orthotropic properties, materials. For isotropic materials, G12 will be equal to G13 equal to G23, and shear modulus is basically the resistance to the angle change due to applied loading. Now, because of these assumptions I've made, and they're quite significant, they decouple quite a bit. So you can see here we set all this to 0. Everything in shade has been set to 0. In fact, all of this here, because of symmetry, is also 0. So all of this here is 0 as well. And so what I'm left with then is these diagonal terms which correspond to shear properties. And those are directly found from this relationship. You can see tau 2, gamma 12 equals tau 12 divided by G12. So S44 here, for example, S66 here is 1 divided by G12. And this right here is 1 divided by G13. And this right here is 1 divided by G23. You can see here how by setting this equal to 0, we've accomplished what we talked about. So if I multiply this row by this column, and these are zeros, clearly this strain, it only depends on this quantity here. And you can see here that this is 0, that's 0, and that's 0. So these last 3 shear stresses don't come even into play. So the normal strain only depends on what's going on with their normal stresses. It doesn't interact with the shear quantities, which is exactly what we wanted. We wanted to come up with a relationship where if I apply shear strain or shear loads, it does not cause a normal strain. And we've seemed to do that by setting all this equal to 0. You can also see here that this shear strain, when it's applied, because these 2 are 0, don't interact with the other 2 shear stresses in the other 2 planes. So far this is quite successful, and now we're left with figuring out how to measure and how to find this 3x3 matrix, because all this is known, and these 3 can be readily measured. To do that, I'm going to perform a thought experiment. And that thought experiment is to apply a load to a bar in the axial direction, one axis. I'm going to use the one axis. And I'm going to apply a load that will stretch this material. And I'm going to measure the axial strain with a strain gauge here. And I'm going to call this epsilon 11. The load applied is sigma 11. And lateral, in the lateral direction, so I want to measure the strain this way, and I want to measure the strain this way. This one here is measuring the strain this way, right? Let me make it more clear. That strain is being measured this way. That's what that one is. This one here, So if I finish my axis, that's 2 and that's 3. So this strain here is epsilon 2,2 and this epsilon 3,3. And I'm going to strain gauge it in each of those directions to measure what's going on. When you do that, and I apply the load sigma 1,1, I apply a load sigma 1,1, and I'll look at the response epsilon 1,1. I'll find it's a straight line for most cases, up to a certain extent, and that slope is the modulus E11. So epsilon 11 equals sigma 11 divided by E11, and E is a modulus. And I'm putting 1,1 because the modulus could depend upon the direction you're pulling the sample. I also want to look at what's going on with epsilon 2,2. And what I notice is when I apply a load in the one direction, I will expect the cross-section to contract. And in the two direction, you will get some contraction as well. So I want to look at what is going on in that direction. So I know it's going to be a fraction of epsilon 1,1, and it's going to be a negative sign. And I know that I'm applying loading in the one direction, and I'm going to say that epsilon 2,2 will contract by the Poisson ratio times epsilon 1,1, and it can be measured. So I'm applying loading in one direction and measuring in the second direction, so I'll put 1,2. And also nu is the Poisson ratio. So when I apply a load sigma 1,1, I can measure the strain epsilon 1,1, and I'll find the modulus of the material. So you will know E11 for sure. Since I measured epsilon 1,1 in the test, I can also measure epsilon 2,2. So I can then take the ratio of epsilon 2,2 divided by epsilon 1,1, and I can get the Poisson ratio nu 1,2. Now, you're used to seeing nu by itself with no nu 1,2, but it's important to realize the Poisson ratio can vary depending upon what direction you're applying a load if it's a composite material. Here, I'm applying a load in the one direction, and so that's why I have 1 as the first number, and I'm measuring the strain in the second direction, so that's why that 2 is second there. And epsilon 1,1 has already been calculated as nu 1,2 times, so epsilon 1,1 is really sigma 1,1 divided by E11. I can now repeat it for epsilon 3,3. Epsilon 3,3 will contract as well, and you can see here that when I apply load 1, it's going to contract in the epsilon 3,3 direction. So negative nu, loading in the one direction, measured in the third direction, and this again it can be found because I can get the strain from the test, which is epsilon 3,3. I can get the strain in the test, which is epsilon 1,1, take the ratio, and then calculate nu 1,3. And now I can plug in what epsilon 1,1 is, which is sigma 1,1 divided by E11. Okay, so that's exactly what I have done here, step by step. You can see that here we've done it for the one direction, and then calculate the strain in the second direction and the third direction. So what I can do now is do the same experiment. So that's the total strain in the one direction, in the two direction, and the three direction for the loading applied in the one direction. What I could do now is I could repeat the experiment. I can repeat the experiment by applying a load in the two direction. And that's a very simple task. All I have to do is repeat this experiment, but in the two direction. And so now in this case, the bar is oriented this way. And I'm going to apply a load in the two direction. And a load of sigma 2, and I'll measure the strain here, which is epsilon 2, and I'm going to measure the strain this way, and I measure the strain this way. And recall how this was the one direction and this is the third direction. So now, this strain that I'm measuring here is epsilon 1, and this strain I'm measuring is epsilon 3. But the primary load sigma 2 should cause a strain epsilon 2, and that strain is going to be sigma 2 divided by E22, where E22 is the modulus in the two directions. And again, that modulus can be different from the modulus E11 when the loading is applied in the one direction. So now I can measure, now if I apply a load in the two direction, there will be contraction in the 1 and 3 directions. So that strain will be a fraction of 2. And I know it's going to be a fraction based on the Poisson ratio. I'm loading in the two direction, measuring in the one direction. And nu1 may not always be equal to nu2 So that's very important. And nu1 may not be equal to nu3 If it's an isotropic material, then they'll be equal. Nu2 is not equal to nu3 necessarily. It can be if it's an isotropic material. And so I know epsilon 2, so it's minus nu2 sigma 2 divided by E22. And I can repeat the experiment, calculate the strain in the 3 direction, and I expect contraction again, and a fraction of epsilon 2. So it's negative, loading applied in the 2 direction, measured in the 3rd direction, and I get negative 2, and substitute epsilon 2, which was found here, as sigma 2 divided by E22. So I've done an experiment to calculate these strains. And when I do that, I fill out the second column. So if I do an experiment only with the stress in the second direction applied, this is what I get for strains. If I do an experiment with stresses in the one direction applied only, then this is what I get. And I can repeat the experiments in the 3rd direction. In the 3rd direction, I can then draw the test sample. And I'm going to apply loading in the 3rd direction, sigma 3. And I'll measure the strains in this direction. And I'll measure the strains going this way. And the strains going this way. And again, epsilon 3 equals sigma 3 divided by E33. That's what I'll find from the testing, and I'll get a new modulus for that. So then I'll calculate epsilon 1, and that strain epsilon 1 is going to be a fraction of epsilon 3. So that's going to be a Poisson ratio. And the loading is applied in 3 directions, measured in 1 direction, and can then substitute what epsilon 33 is, which is sigma 33 divided by E33. I can then do the same thing for epsilon 22, which is going to be a fraction of epsilon 33. So minus nu, loading applied in the 3rd direction, measured in the 2nd direction, and I get this. And so now I can look at what happens when stress is applied only in the 3rd direction. And when I look at the total strain, I get the total strain is a stress in the 1 direction. If I apply all stress simultaneously, all 3 stresses simultaneously by the principle of superposition, and after doing this virtual uniaxial test on each of these directions, I can superimpose and calculate the total strain. And when I do that, I get this. Now note that I can put this into matrix notation. So now you don't have to pay attention to this at all. Sorry about that. That's a mistake. You don't have to pay attention to this anymore. These strains are additive. And that's what I intended to show. And what I want to do is then isolate this when I write it in matrix notation. And when I do that, I get the 3D orthotropic properties like this. And all these quantities can be fully measured. And because the stiffness matrix has to be symmetric, then it follows that this should be equal to that, and this should be equal to that, and this should be equal to that. And so this relationship has to manifest itself. And all these properties can be measured. The modulus can be different all across, and that's not a problem. These modulus can be different. All the Poisson ratios could be different. But this relationship must hold. We can invert the relationships to get this. And the bottom line, you don't have to be worried. Like, these numbers will be fully known after the test is done. After all the testing is done. And when you invert the relationship, you get a massive relationship, which MATLAB or Mathematica can do. Again, do not worry, this is done by computers. But the bottom line is, we have a way of relating stress to strain. That's what matters here. And again, the Poisson ratios are all equal to nu for isotropic case, where like aluminum or some other metal where the properties are not directionally dependent. So for the isotropic case, this is what you get. This is a relationship we get. Only E and nu are the ones that need to be measured. And this relationship here will simplify to this for the isotropic case. By setting nu1 2, nu2 1, nu1 3, nu3 1, nu2 3, nu3 2 to nu, and by setting E1 1, E2 2, E3 3 to E. You can add the thermal effects in here, and to do that, you have the coefficient of thermal expansion. What I've done, I'm showing you the inverted version of this again. So here you have the strain equals this. This is what I've been showing you. I showed you that for 3D orthotropic materials. So I already showed you this for 3D orthotropic materials. And I'm adding this term here as nu. This term accounts for thermal effects. And so that's a coefficient of thermal expansion, which can be measured. And delta T is the temperature, final temperature minus the stress-free temperature. And this is the column vector, this is the way it looks. You can then invert this whole relationship, and once you do that, you get stress in terms of strain, and this is what you get at the end. So, the material properties, typically, most materials will have a slight volumetric change. So you're going to have a contraction. Incompressible materials will have almost no change in volume, like rubber. And the Poisson ratio will be close to 0.5. Most aluminum metals will be close to 0.3. The shear modulus can be determined to be a function of Young modulus and Poisson ratio using this relationship. So if you know Young modulus and Poisson ratio, you can calculate G. In other words, if I have an isotropic material, from a uniaxial test in the one direction, I can measure this strain and I can measure this strain. So not only I'll get the modulus E, I will also get nu, which is this one right here. I'll get nu because I'll know epsilon 1, I'll measure epsilon 2. So I can get nu, and if I know E and nu, I can get the shear modulus. And so then when I do a torsional test, I better get a comparison that matches. This must hold basically. Simple tension case, this is the way it looks. You apply a tension load and the remaining items are zero, and basically your strain becomes this. And I already shown you that this is what happens. When you apply a load in the one direction, you get a strain in one direction but contraction in the other directions. In the pure shear case for torsion, for example, you then get shear strains instead. And I'm using the term mu, but in fact here, what you have here is that mu is equal to G. So this mu is equal to G. For hydrostatic compression, you can also look at that one. Basically, in this case, you have compression load applied equally into the elements. And when you actually run this calculation here, so if I were to then substitute this for minus P, this for minus P, and this for minus P, and do not account for thermal effects, I make this equal to 0, 0, and 0, then you get what I was showing you now, which is the hydrostatic compression case, and you get this relationship. But I want you to notice how the volume change, as we talked about earlier, is the summation of the column of these diagonal terms. And so the volume change is 3 times 1 minus 2 twice nu divided by E times the pressure load applied. That's what you see there. And we can actually determine the measure of volume change by calculating something called the bulk modulus, which is the inverse of this coefficient. So if I have a sample and I subject that to uniform compression load in P, I can calculate how much the material is willing to change in volume. Because we say that this summation of the diagonal terms is equal to the change in volume for a cube. And so this measures the bulk modulus and is also related to E and nu. Here's a relationship of how all the different elastic constants, and I didn't cover them all, but K here was covered. Mu is G, and K is the bulk modulus. And I didn't cover lambda, which is okay with me, but I want to make sure you know that you can relate E, nu, K, and G with the other constants on this column. And if I'm interested in relating E, so E and nu can be related to mu, for example. So you can use this table to find out how to relate everything together. Here are typical values of elastic moduli. I think it's worth remembering some of them. For aluminum, in British units, is usually 10 MSI, in GPa about 70 GPa. The Poisson ratio, as you can see, varies anywhere between 0.2 and 0.3. Metals, usually in the 0.3 range, and rubber is close to 0.5 because it's incompressible. You can see that here, if I make nu close to 0.5, what happens to the volume change? The volume change is almost zero. So the bulk modulus is almost infinite. And so, yeah, so rubber materials will typically result in almost no volume change. And here is the other constants. Here is the coefficient of thermal expansion. This is more so you can see how the different materials relate with each other.
Let's discuss how we will go ahead and solve these equations. So we have three governing equations, and these three governing equations came from second Newton's law, where we had body forces, accelerations, and tractions applied, and we were able to use Cauchy's relationship to relate the tractions on the surface to stresses inside the body. And from there on, we were able to then use the divergence theorem to then develop these three equations of elasticity that represent the three equations that will render the system in equilibrium. And as you can see here, we have three equations and six unknowns, and the six unknowns are the stresses, sigma xx, sigma yy, sigma cz, which are the normal stresses acting on a cube, and sigma xz, sigma yc, and sigma xy. These are the shear stresses. Together, the six stress components at a material point react the external forces applied on the structure. And the six stresses will vary across the body, the aircraft, the launch vehicle. And then we went on and developed the six strain deflection relationships. Three of them describe stretching of a cube, where U, V, and W are the deflections in the X, Y, and Z directions. We then have the shear strains, which represent the angle change. And as you can see here, we have six equations, and we have three unknowns here, U, V, and W, and then six strains that are unknown. And finally, we have then the stress strain relationships. The stresses must be related through the strains using the constitutive equations. And the six stress strain relationships are given by this equation here. We used virtual tests to develop what the stiffness matrix will look like. So in total, we have 15 equations, 15 unknowns, six stresses, six strains, and three deflections. And as you can see, that's quite difficult to solve. We also talked about boundary conditions. We have this situation where we can apply traction forces on the surface of the body. It can be either pressure or tangential force like friction. And then we can apply kinematic boundary conditions. Deflections are fixed on the boundary, like a clamped condition. We can specify either tractions or deflections, but we cannot specify tractions and deflections at the same location. So for example, at this location, we have the boundary fixed. We can't possibly also specify tractions at the surface. Generally speaking, we can then take these tractions and relate them to quantities inside the body. And what is the goal? The goal is to be able to take a CAD model, ideally apply a load, and then be able to determine the stresses that form in the body. And these stresses are the ones that are reacting this external load. And you can see the stress can vary across the system. That would be the dream, is to go from a CAD model, apply loads, and then suddenly be able to come up with this stress field and then be able to predict failure. For example, here, red signifies high intensity stress. And so there's likelihood of potential failure at this location if the stresses are high enough. So how do we come up with that approach? How we compute deformation stress and failure load given a load applied to the structure? Well, so we have the 15 equations and we have the 15 unknowns. And there's a mistake here, there should be 6. We have the equilibrium equations, 3 of them. We have the constitutive law, we have 6 of them. And then we have strain-deflection relationships, which are 6 of them. And then we have these 15 unknowns, deflection, strains, and stresses. So 15 unknowns and 15 highly coupled equations over complex domain. You can solve these equations using hand calculations for simpler geometries. We can put all the equations into one single equation. For example, I could use a stress relationship here, and I can plug in strain for deflection. So I can take this whole expression here, which is in the book for this course. We didn't discuss these nonlinear terms, but for small strain approximation, this is what we're going to be using. And anywhere you see ij, that's basically I equals either x, y, and z, and j is either x, y, and z. So you can basically come up with the different combinations of strains that you can have. And so you can plug in this deflection relationship into this equation, and then plug in sigma ij back into this equation, and everything can be in terms of deflection. So yes, you can reduce the 15 equation down to just 3 equations, but nevertheless, they'll be highly complex. And so what is this other solution we may have to be able to solve these equations? And that brings us to finite element modeling. Finite element modeling resolves the complexity of having to solve these equations. You have this CAD model, and we take this CAD model and we break up the CAD model into elements. We call it elements because I've taken this domain and have divided the domain into subdomains. And these subdomains will have either a triangular shape, a quadrilateral shape, and if I go to 3D structures, I can discretize the subdomains into tetrahedrons and hexagons. And generally speaking, when you do this discretization, we know that we have infinite number of material points here, but when we go from this domain to these subdomains, we have a finite number of subdomains. And these subdomains here, these triangles, are called elements. So that's why it's called finite element, is because we have discretized the domain into finite number of subdomains. And so what I've really done then, I have broken up this continuous structure into discrete subdomains, these triangles triangular pieces. And the idea here is then to take every single of these triangles, which could have different shapes, and map them into a master triangular element, which is going to be the same shape for every element. So what I'm going to do is to try to solve the partial differential equation, these highly complex equations, for the master element that has a shape. And I'll go ahead and map each of these triangles into the master element, and then after I do that, I will then connect these elements together. So the idea here is to solve the PDEs, the partial differential equations, for every element using the one master element, and then I'll connect the elements together via nodes. So these triangles come at some vertices, which I'm going to call nodes. And at these nodes is where we're going to be calculating deflections. And the idea here then is to approximate the solution of this discretized model. So why use finite elements? What is the point of using finite elements? Why do I need to really learn the basics if I can let the computer do the work? And the answer is that simple models are crucial for checking and understanding simulations. And also, you don't want to be using finite element modeling for initial sizing because that'll be time consuming. You want to do the sizing using hand calculations as much as possible, and then refine the finite element solutions, um, the solutions to the problem, the design, using higher fidelity models like finite elements. And simple models are really the only way to create a physical understanding of the problem and to check the results. So let me go through the process. I take the CAD model, discretize it into either triangular elements or quadrilateral elements, and that can be first order elements or second order elements, meaning I can interpolate linearly or quadratically. The higher order the element, the more accuracy I'm going to get. And again, this is not a finite element modeling class, although we're going to do some finite element modeling. However, I am giving a top level view of what finite elements is really trying to do. And so we then go and discretize a model into subdomains using triangular or quadrilateral elements. And then I take this model and I apply loads to the model and boundary conditions, and I specify material properties. So I configure the model in this step. The previous step is called meshing because when you basically have a CAD model and discretize it into elements, that process is called meshing. In this case, we're pre-processing the model by applying the loads and the boundary conditions and the material properties. Then we're going to submit this model into the solver. And what we're really doing with the element formulation is that we're taking these 15 equations and basically taking these highly coupled partial differential equations and putting them in this form: stiffness times deflection equals external force. Now, this is a mathematical miracle. Why? We've taken complicated equations, they're very complicated to solve by hand, and I have taken that and put it into a linear algebraic form that can be solved quite easily. The forces are known, we know we apply them. The stiffness matrix is known because the stiffness matrix depends on the material properties and it depends on the geometry and the number of elements and nodes and all that. So K is fully known and F is fully known. So all I have to do now is solve for deflections by inverting K. And if I know deflections, I can then calculate strains. And once I know strains, I can calculate stresses using the constitutive relationships. And these stresses can then be used to then determine whether the structure will fail or not. And there are two kinds of analyses, and there's many more, but these are the two top level analyses that can be performed. One is a static analysis, which will give you the deflections, strain, and stresses. And then the dynamic modeling, which will give you frequencies and mode shapes. What is interesting about finite elements is that with finite elements, not only you can visualize the stresses and strains over the body of the material, which could vary across the body of the material, but you can also visualize how the structure deformed and deflected, which is very, very useful to understand whether the modeling is correct or not. Secondly, I want to point out that it is a huge mathematical miracle to take highly complex equations and be able to synthesize it into a simple linear algebra problem. And that is quite impressive approach that finite element methods has given us. If I go a layer deeper now into what's going on, this is an aircraft finite element model, and it probably has over 100,000 elements, although some models can have up to a million elements. In this case, what you see here is a CAD model was provided, a mesh was created, meaning that we have divided and discretized the domain into subdomains. And again, it's called finite elements because I have discretized the domain into a finite element number of subdomains. And once I have this mesh created by selecting either 3D or 2D models as 2D elements as is appropriate, I'll then apply the loads. And the thing I want to point out here, in this case, if the aircraft is flying, you don't really have a fixed boundary condition. And that's quite exciting. The aircraft is flying in the air, and the only boundary condition is really the fact that when the aerodynamic loads are applied to the structure, the only thing resisting those loads and reacting those loads are the inertial effects, MA, mass times acceleration. Then I have the boundary conditions which could be applied. The material properties, you could have composites, aluminum. You can specify some areas to be sandwich structure, some areas could be metal. You can basically select the areas that should be corresponding to the material properties of interest in the area. And we already covered geometry. Once you have all those things defined, you can then submit it to the finite element processing. And the idea here is then to interpret the results. And what is quite incredible, and I want to repeat it one more time, is that you could have millions of degrees of freedom. And these 15 equations and 15 unknowns in a partial differential equation will be highly complicated to solve over an aircraft, especially when you have a very complex shape like this one. Just imagine trying to solve it for even a simple cylinder. That would be very complicated. But we're able to perform a mathematical miracle and turn the problem into stiffness matrix times deflections equals force. And the force is known, the stiffness matrix is known. I can calculate the deflection. The stiffness depends only on the material properties and geometry. And I can then invert K to get U. Once I have the deflections U, V, and W, I can then calculate the strains. And to remind you, if I have U, V, and W, I can calculate the strains. Once I have the strains, I can calculate the stresses via the constitutive relationship that we have developed. So the next topic I want to cover is the stress and strain transformations. And why is that's useful? Sometimes we need to transform stresses and strains to predict failure. That's one possibility. It is useful to transform strain measurements into useful quantities. And it's also, for example, if I make strain measurements, I want to be able to determine what the structure is doing. And perhaps you want to transform those strains to be able to use them for further calculations. We can then also use transforming stresses and strains for analyzing composite materials. Let me go into the theory of transforming one coordinate system to another. So say I have this global coordinate system 1, 2, and 3. So I have the 1 axis, the 2 axis, and the 3 axis. And I want to perform a rotation about the 3 prime axis. So I'm going to create a new coordinate system 1 prime, 2 prime, and 3 prime. And I want to relate the stresses in the 1, 2, and 3 system. I want to relate those into the 1 prime, 2 prime, 3 prime system. One important thing that you may have to do is to develop something called the direction cosine matrix. In here, you're going to calculate the cosine of 1 between 1 prime and 1. In this case, that represents the angle between 1 prime and 1, the 1 axis. And then you're going to calculate the cosine between the 2 prime and 1 axis. So these 2 prime and the 1 axis. The cosine of 3 prime and 1 axis in this example is this one, this 3 prime and the 1 axis, and that angle is 90 degrees. The cosine of 90 degrees is 0, so in this example that's 0. And as an example, I want to calculate the cosine of 3 prime and 3. So that's going to be this angle, the difference in angle between these two axes is 0, so the cosine of 0 is 1. Here's an example more specifically. We have a rotation of 1, 2, 3 to 1 prime, 2 prime, 3 prime of rotating about the 3 axis by an amount alpha. I'll let you do this at home by pausing this video, but I think you can be able, you should be able to show that the angle difference between 1 and 1 prime is basically 180 minus alpha. And the cosine of that is going to give you alpha. So I invite you to go in and perform the calculations and see if you're able to get that. And then you can then go on with filling the rest out, but that's an example of rotating about 3. Now a more general rotation is going to look like this. I have the x1, x2, and x3 axis, and I'm going to rotate that coordinate system into a completely different, not just rotating about the 3 axes, but I'm going to rotate about all axes. So I'm going to have the x1 prime, x2 prime, x3 prime axis. And I'm going to rotate it from this coordinate system into the red one here, denoted there. So you have to basically do the same calculation. You need to calculate the cosine between the x1 and x1 prime axis, and that'll be L1. So in this example, we have to calculate the difference in angle between x1 and x1 prime as an example. And you want to do the rest of them also, n1, n1, and so forth. Once you get the cosine calculations between the angles here, you fully populate this, and I'm going to label this as Qij. This is just basically saying that Q11 is this, Q12 is this, Q13 is this, and so forth. You can then the transformation formula is given by this. So the stress in the x1, x2, and x3 is going to be this stress here, stress PQ. This stress is known, fully known. The 9 components of stress for that is known. And you're going to then do this multiplication to get the stresses in the new coordinate system. I have expanded it here for you. And what I want you to notice is that sigma x, sigma y, sigma z, tau xy, tau yz, tau zx, those are known quantities in the x1, x2, and x3. And what I'm trying to do is find the stresses in a new coordinate system. And so I have to perform these calculations. And therefore, I have to get the direction cosines to be able to do that. And basically, I have to find the cosine between these axes to make this happen. I can show you that expanding, how to expand this in a second, but it's fairly simple. INJ is known, and so you basically want to expand on this, and I'll show you how to do that. But just keep in mind that Q11, for example, is L1, and L1 is cosine of x1, x1 prime. So that's the important thing to understand, that Qij is basically a component that goes here, and all you have to do is plug that into this equation here. There's 9 equations here in total. Let me show you how to expand on that. So I have sigma j prime, and anytime you see that, what we're really saying is that with INJ fixed, we have summation from P1 to 3 and Q1 to 3. And all I'm going to do now is expand on that equation. And that's fairly simple to do. As an example, I can do sigma 1, 1 prime. And sigma 1, 1 prime is the summation from Q1 to 3 and P1 to 3 of Q1P, Q1Q times sigma PQ. And all I have to do now is do this expansion. Like, for example, the first term will be Q11 times Q11 sigma 11. Or we've been using the term sigma XX. It's the same thing. Plus Q1, 2, Q11. Sigma 1, 2. And this is the same thing as sigma xy. And then you can keep expanding. There will be 9 components. And as you can see here, I know Q11, which is this term. I know Q12, which is this term, because that's the angle between the axis x2 prime and x1. And so that's how you will approach that. Now, let's say I only have a rotation about the z-axis. You can use these equations fairly simply, and all you have to do now is calculate the direction cosines. And when you do that, you get this equation here: cosine theta, sine theta, 0, minus sine theta, cosine theta, 0, 0, 0, and 1. And this should be fairly simple to calculate based upon what we learned so far. And what I will do now is insert this into this expanded notation here. And you can see here that I'm only looking at 2D stress transformations, so sigma z is 0, and as a consequence, this term is 0, this term is 0, this term is 0. And so all you're left with is these 3 terms which were shown in that page. So this should be fairly easy to develop, and these are your 2D stress transformations. In other words, if I know the stresses in the XY coordinate system. I can calculate in the new coordinate system, I can calculate the stresses in that plane. If I were to take an example, I have this uniaxial bar and I apply a load in the X direction. I can then calculate what will happen, what is the stress as I rotate this square into that square by an amount theta. So I'm going to rotate it by an amount theta and then determine, I'll determine how that stress, that normal stress to that face, and that traction that's tangent to that face going to change as I rotate this cube, this square. And I can use this relationship right here and determine that. In this example, sigma y is 0 and I don't have any sigma xy. So this is 0 and that's 0. This is 0 and that's 0. This is 0 and that's 0. So you're left with just these terms, and I'm only plotting this term and that term. You can see that's exactly what we found here, and I can plot that. And as I rotate theta, you can see that the shear stress changes and the magnitude increases up to a 45-degree and then draws back to 0 here. Of course, there's no shear stress when theta is 0, and you will not expect any shear stress when theta is at 90 degrees. Very similarly, I can transform the strains in the similar manner. I can use the same formulas to transform strain. As long as I can find the direction cosines, I can then do the transformation. In a very similar manner, we can expand it all. The 2D strain transformation follows very simply by setting epsilon z, epsilon yz, and epsilon zx to 0, and then I can use the rotation by theta to then determine this transformation. So knowing epsilon x, knowing epsilon y, knowing epsilon xy, knowing those quantities in the x1 and x2 and x3 coordinate system, I can calculate it in the new coordinate system x1 prime, x2 prime, and x3 prime. And these are the equations that you will find if I do a rotation about z of amount theta. And finally, I can use this approach for strain measurements. Strain measurements are typically done by bonding strain gauges, and we can then measure the electrical resistance of the filament with changes in strain and measure electrical resistance across a Wheatstone bridge. And here's an example of 3 strain gauges that have been installed at an angle theta A, theta B, theta C. And what is incredible about this is that I can measure the strain along A, and I can measure the strain along B and along C using these gauges. So I know this strain, I can measure this strain, and I can measure this strain. And the important consideration here is if I know those strains, and I know the angles of those strains, gauges, the way they're installed, then I can use the transformation relationships provided earlier to come up with these 3 set of equations. Now, I know theta A because I know at what angle I install the gauge. I know theta B and I know theta C. So I know all these guys here and these guys here. And so now I should be able to, knowing epsilon A and epsilon B and epsilon C, calculate epsilon x, epsilon y, and gamma xy in the xy coordinate system, in this xy coordinate system. I should be able to calculate those strains. And so that's how you can use these measurements, these transformation equations, is to get the strain field in the XY Cartesian coordinate system. Other coordinate systems do exist. I want to point out to the cylindrical coordinate system. Here, I have x1 and x2 as a Cartesian coordinate system, but I want to express what we're looking at here. So if you have a body of material that revolves about the z-axis, then ER is the radial coordinate system, theta is the tangential coordinate system or circumferential coordinate system, and z is the coordinate system that coincides with the axis of revolution. The strains will be just that. UR represents the deflection in the radial direction. U theta represents the deflection in theta direction. And UZ represents the deflections in the Z direction. And the strain deflection relationships are going to look like this for a cylindrical coordinate system. And again, I still have 6 components of strain, and I have the 3 components of deflection. I also have the equilibrium equations in the cylindrical coordinate system, and I want to point out that it's going to follow the same convention we discussed before. The Z face is going to have a sigma Z pointed outwards from that face. This face here corresponds to ER, this ER right here. So the stress normal to that face is sigma R, the radial stress. And then I have the hoop stress, which is circumferential stress, sigma theta. And then I have these tangential stresses that are shear stresses on these faces. So same convention as before, the stress can be written in this stress tensor. And the equilibrium equations will look like this, where FR, F theta, and FZ are the body forces. Later on, when we discuss cylinders under pressure, we will be discussing sigma theta, which is a hoop stress, and sigma Z, which is the axial stress. We can also use a spherical coordinate system where theta, phi, and r are the coordinates of the system. And so in this coordinate system, sigma r is a radial stress, sigma phi and sigma theta are the circumferential stresses or tangential stresses. And again, I'm going to have 6 components of stress. 3 of them are normal, and the rest of them are shear. And I'll use the same convention as the one when we discussed the cube. The equilibrium equations are given by these 3 equations, and FR, Fp, and F theta are the body forces. And then I also have Hooke's law, and as you can see in Hooke's law, it doesn't matter what coordinate system I'm using, we still are going to, Hooke's law is the constitutive law we showed earlier. Those constitutive law equations are still valid. These equations shown here are the same equations we showed earlier, but in a more compact fashion. And I want to point you to that so that you can remember it. Right here. So this stiffness matrix stays the same. Doesn't matter what coordinate system you're working on. It's invariant of the coordinate system used. And in Hooke's law in spherical coordinate system also looks the same, and you will expect so. And Hooke's law is the same as the constitutive law that we derive using the virtual test. So I hope you have a great day.